Okay, I welcome all of you again. This is our afternoon session, the last session of this event. I should say that we are most delighted having Gregory Gabadadze from New York University to join us on this. He's a very busy man, but he found the time to come. Gregory had outstanding contributions in everything related to gravitation. Although he did not start from gravitation when he was, Gregory was a Glennis Farrar student. It's a good story of his and so on. So now he is a Dean of Sciences in New York University, Vice President in Simons Foundation. His work on gravitation, on many different forms actually, is very renowned. Probably most famous is DGP,
whatever.
DGP, yeah. And he will talk today about another important thing, and I understand it has something to do with anomalies, which is a new object for me.
Yes.
I welcome Greg, you one more time. You are not first time here, but thank you so much for coming. Okay.
Thank you so much, Samson. Well, it's a great pleasure to be here. Hello, everyone. It's a delight to participate in the celebration of Sir William Hamilton's birthday celebration and also the HMI Jubilee. I'm going to talk about things which rely very heavily on action principle. I guess that's the connection with the Hamilton's work. That way, Hamilton is at the foundations of everything that I'm going to be talking about, and once in a while I may even reference Hamiltonian, even though we typically use Lagrangian, but we think of Hamiltonian. Hamiltonian is energy, while Lagrangian is enabling you to do more invariant formulation, Lorentz invariant formulation, as opposed to the Hamiltonian, and hence the preference. That said, I'll be talking about quantum modifications or quantum corrections to classical Hamiltonians that Sir Hamilton used. And some of those corrections, I will claim, are very important in the context of anomalies. So anomalies are quantum effects. Maybe I will outline them briefly for the part of the audience who may not be familiar with that. And the question will be, how do we write effective actions which incorporate those quantum effects already at the level of what we write as an action, so that we can just do variational principle of that quantum modified action and get all the equations, all the PDEs that we'd like to solve, as opposed to rely on classical action and then calculate quantum corrections as loop corrections and so on and so forth. So this is based on a number of works. The one in 23 that I wrote, and then followed collaboration with Massimo Porati, David Spergel, Georgi Tuhashvili, and there is a work in preparation. All right, so here is my outline. I'll try to go slowly, pedagogically, as much as I can. And for that reason, I will start with a simplified model. This is two-dimensional theory, 1 + 1 dimensional quantum field theory, named after Schwinger. It's just Maxwell's electrodynamics, devoid of any complexities of four-dimensional world. And the beauty of that theory is that you can ask any question that you are interested in and get an exact answer because it's exactly solvable. So I'll be asking some particular questions related to how do you incorporate quantum anomaly in the effective action of the theory, which, by the way, happens to be exact. After that, I'll go to discuss similar things in the context of Einstein's gravity, which is a lot more complicated, as you can imagine. Nevertheless, there will be some similarities to what I say in the two-dimensional case, and the similarity will be that essentially anomaly forces us to have some additional degree of freedom, some additional scalar degree of freedom, and we'll be studying dynamics of that degree of freedom. So initially, I'll introduce something that was done by what's called Rigert, actually, because it was done by Rigert. At the same time, it was done by Efim Fratkin and Zeitlin, but it carries only Rigert's name historically. And I'll outline what the problems are in that approach and how they can be solved. So once you solve those problems, that gives rise to certain new physics, and the consequences of that physics will be explored in the context of holographic description, but also in the context of cosmology. In particular, I'll talk about how inflationary theory gets certain corrections due to the additional degrees of freedom, and how those additional degrees of freedom may lead to formation of primordial black holes, but also in some other domain of parameter space, how that degree of freedom can also act as dark matter by itself. And by the way, today is also Einstein's birthday, so I'll be talking about Einstein a lot. So, all right. So the first equation, that's an action for 1+1 dimensional electrodynamics, one spatial dimension, one time, called the Schwinger model, because Schwinger was the first one to think about that carefully and exactly. And you see the Maxwell term, which is divided by E squared. That's somewhat unusual notation, perhaps, as compared to classical E&M book notations. Nevertheless, it's a convenient notation. It's just rescaling of your gauge field, photon. So that's the Maxwell term. And then the next term is just the Dirac term for a 1+1 dimensional Dirac spinor called psi. And D hat stands for the covariant derivative with the corresponding gauge field. And it's a massless fermion. That's what the Schwinger model is. Now, that theory has two global symmetry groups. One is responsible for conservation of charge. That would be U1 vector. That's just the phase rotation of that fermion. And then there is another symmetry, which is kind of chiral rotation of that very same fermion. That would be e to the I gamma 5 alpha, which is responsible for conservation of helicity. And that exists there because the theory is massless. What happens in such cases very often is that you cannot maintain both symmetries at the quantum level. At the classical level, they are present. At the quantum level, you start calculating correlation functions, and you enforce certain what's called word identities. Those are consequences of those symmetries, and you cannot enforce because quantum corrections modify them in a way that only one is enforceable. And well, for I was going to say obvious reasons, but for physical reasons, you maintain the conservation of the vector current because vector current here is coupled to the gauge field, and you don't want to have currents coupled to gauge field to have anomalies. Otherwise, you will have to go to Samson's work with Fadeev as to how to deal with those sorts of theories. Those are complicated theories, and Anton Alexeyev is also here. They've written some foundational work on quantization of anomalous theories or what they mean. So in this approach, we keep that as conservation while you give up on conservation of the axial current. And next equation that you see is just the derivative of the axial current, which on the right-hand side has something in general non-zero, and that's the only equation in which I'm going to use h bar. I dropped h bar in equation above, and I'm going to drop it in every single equation, or maybe almost every single equation afterwards. But that's just to signify that that's a quantum effect. Comes from one loop Feynman diagram for those who study quantum field theory. And subsequently, I'm going to put h bar equals to 1. If I want to take the limit that Maxim Kanchevich was taking yesterday, for me, that limit would be large action, right? So large action would mean that my h bar is very small, essentially, although I put it of order 1. All right, so what I'd like to do is now to rewrite the theory so that this equation, that equation is captured as a variational equation, essentially, because here it's not a variational equation. If you just take literally the derivative of the left-hand side using the equations, classical equations, you're going to get 0. But then only the loop correction that modifies it. But I want that to get, right there at the level of the action. So for that, I will integrate out fermions. This is what I mean by that. You can think of quantization of the theory, and the convenient way to think of quantization is a path integral, Feynman's path integral. So what you see here is part of that path integral, in which I already retained integration with respect to the fermions. You can notice that that integral is Gaussian. You can just integrate. You will get determinant of the Dirac operator. And once you exponentiate that determinant, that will define correction to your Maxwell term, and that's your effective action. Now, because this is 1 plus 1 dimensional and everything is known about that, you can calculate the determinant exactly. I didn't put the references because this is more general talk, but there are people in the mid-'80s, with all due respect to them, they've calculated that exactly, and you can write the result of calculation in the form that you see up there. Again, the Maxwell term, and then you have something else, and that something else looks non-local, right? So it's, again, the field strengths, F carries 2 indices. I'm just not writing indices for simplicity. And those 2 indices are contracted with the other F, and there is one over D'Alembertian in between. And that has its own reason as to why you got terms like this. It's simply that one-loop diagram. It has transverse structure with appropriate powers of momentum, which are determined by the fact that your coupling constant in this theory is dimension full. And therefore, you get that expression. Now, the reason why it looks non-local is because I insisted for the full effective action to be written in terms of the gauge field only. But actually, there is nothing non-local about that. It's just the consequence of me not introducing proper degrees of freedom that actually describe that theory. And the line below is essentially reintroducing the degree of freedom which you need in order to write that theory in a manifestly local way. And that's a scalar field phi. So then it's very easy, actually. If you write down the scalar equation and express scalar from that equation, you'll get back the first line. But the goal is actually to get the anomaly equation of the previous slide. And the claim is that the third equation that you see on the slide is precisely the anomaly equation of the previous slide. And how it is, I'll tell you. So the right-hand side looks like of this equation, but left-hand side has in it box of phi. In this theory, there is what's called a bosonization. So every single operator written in terms of the fermion fields you can express into the boson fields. And axial current is actually d mu of phi. And box of phi would be derivative of the axial current. And hence, this equation, the last one, is equivalent to the equation of the previous slide. So this achieves the goal, right? So what I wanted is to have an action such that I take variation of that action, classical one, and all the equations that I get already has in it, having them anomaly, and that's what it is. So the price to be paid for that is that I had to introduce some degree of freedom. Well, in fact, that degree of freedom is a very physical degree of freedom in this theory. It's known, actually, that this theory is the theory of that degree of freedom. It's a massive degree of freedom in the end. So the lesson learned is this. So for anomaly, if I, to be captured in the action, if I insist on formulation of the theory only in terms of gauge fields, then it would look non-local. In order for it to be local, I would have to introduce some degree of freedom, which is a physical degree of freedom. And the third lesson, which I didn't emphasize, if I wanted to write this theory again as higher dimensional theory, in which case 3, then I still can write it as a local effective theory. It will be Chern-Simons theory, actually. If I start with 3-dimensional Chern-Simons theory and kind of took it naive pull back onto a surface or a line, rather, so I would have gotten this theory. So those are the lessons. So non-locality, or you have to write it in higher dimensional way, or additional degree of freedom, and all of them are connected to one another. Now, there are other examples which repeat this story, essentially. I won't go into them. They are well known. This thing is also well known. I will just mention for, there are some experts in the audience. If I were to do the same thing for axial anomaly in 4 dimensions, there would be what's called Westomino-Witten term. That does precisely the same job. You have a scalar which couples to the topological number density. Or if I were to do the bosonic string theory, look at it as 1 plus 1 dimensional field theory, and look at the scale anomaly, I would have gotten exactly the same story. This was done by Polyakov long ago. So you would write effective action, which captures that scale anomaly. And if you insist only on gravitational fields, it will look non-local. But to make it local, you have a scalar degree of freedom that writes it. Sure. Exactly. So in two-dimensional, yes, Samson is pointing out that in two-dimensional cases, we can do everything exactly, while in 4 dimensions, those are approximations. So I would like to apply that to 4-dimensional world, real world of gravity with Einstein's theory. And before we plunge into any sort of equations, you may ask, what could that scalar be to begin with? And so this picture zooms your attention on something that is well known. Many of you use it. It's called the scale factor, or the conformal mode of graviton. And here is a dichotomy. You know that general relativity, Einstein's theory, has in it only 2 physical degrees of freedom. So gravitational wave, classical wave, has 2 polarizations only, or if you quantize, graviton has only 2 helicity states, but nothing else. Everything else is either gauge artifacts or removable by certain constraints, which are very cleverly encoded in Einstein's theory, actually. That's how it's very remarkable. Nevertheless, in the context of cosmology, we all use what we call the scale factor. And scale factor is something that describes the expansion of the universe. In fact, if you want to measure a distance between 2 observables in an expanding universe, so that's how you measure it. So those red points represent some observables, let's say, and the universe is expanding as that balloon is expanding, and the distance between them is just what's called comoving distance. That's a kind of fixed coordinate object multiplied by the scale factor. So if scale factor grows, the physical distance grows. So it's physical. On the other hand, it doesn't have physical fluctuations. If you just work out, let's say even in a Minkowski space, work out what the fluctuation of that conformal mode is, which is this conformal mode, so you'll see that it's constrained by the equations that you get from Einstein's theory, and hence there is no wave corresponding to it. So what I will claim is that once you take into consideration those anomalous pieces in effective theory, you will have to have some degree of freedom, which actually is very much connected with the scale factor. In fact, in some cosmological backgrounds, it is the scale factor. And that will be the object that I'll be talking about a lot. So this is the action of general relativity. I already wrote it with D. That means D space-time dimensions, although I'm interested in 4. And first term is the Einstein-Hilbert term. Capital M stands for the Planck mass. I don't use subscript. Well, it's actually square root of, M Planck divided by square root of 2. And then you have now 4-dimensional Maxwell term, 4-dimensional Dirac term, 4-dimensional scalar. But you can include whatever you would like. Let's say that's a standard model, or your favorite beyond the standard model theory. Any of that doesn't really matter. So as long as those are conventional, spin 0, a half, and 1 fields, spin 1 fields, quantized in a conventional way, that's this conversation applies. And then it's been known for a long time. I have reference on the next slide. Somehow I missed on this one. Since mid-1970s, it's been known that there is a gravitational trace anomaly. What that means is that if, let's say, for simplicity, those fields were massless, then there is scale invariance related to that sector of the theory, and you would expect that energy momentum tensor of the particles is traceless, because that's equivalent to the statement of conservation of the dilatation current, right? So which is a consequence of scale invariance. However, once you go into the loop calculation, you will discover that it's not traceless. On the right-hand side, you will get something which is, in general, pretty complicated. These terms are known and named. The first one is called the A term. So it's a coefficient A, little a, multiplied by Euler density. That's the Euler density. First one is a combination of Riemann tensor, Ricci scalar. And the second one is, I call here omega. In 4 dimensions, it's equivalent to the Weil tensor squared. Excuse me. But in general, actually, it's that combination. Riemann square minus twice Ricci tensor square plus 1/3 of Ricci scalar squared. And that's what you get through calculations. Now, I need to emphasize that even if I didn't have scale invariance, let's say fermions were massive and the scalar was massive, that's all fine. You would have had something on the right-hand side related to those masses, that would be explicit breaking of your scale invariance, but this anomaly term would still be there, okay? So it's in addition to whatever explicit breaking you have of your scale invariance, this is in addition to it, so it's remarkable. Now, coefficients A and C are both proportional to h bar, but I'm not writing it explicitly, as I said. And they are also proportional to the number of particles that participate in those quantum loops that give rise to that scale, gravitational scale anomaly. So all of them, spin 0, spin 1, spin a half, contribute with the same sign, actually, to it. And A and C are just some combination of those numbers. Right, so the question then is, can I write down the gravitational action so that that scale anomaly is already encoded in that action? So the second line, as you can see immediately, contributes to the Einstein's equation, trace of the Einstein's equation, Ricci's scalar times Planck square would equal to what you see on the right-hand side. The answer is yes, but in order to get to that answer, there is some history to go through, so I want to go through that, not because of the sake of history, but also it's very instructive, and also it brings to the new point that I would like to discuss, actually. And I said in mid-70s, this was calculated by Kapper and Duff, and then Duff kind of generalized that. So you start in the simplest case with one loop diagram, and the outside external wavy lines are the gravitational lines, while internal line in that loop, it can be any of those quantized spin 0, half, or 1 fields. And well, there are divergences, so you know how to renormalize that. And by the way, I should say this is an effective field theory. General relativity is not a renormalizable theory like Maxwell's theory is or Youngman's theory is. Nevertheless, there is a meaning of renormalization of it as an effective field theory that's an expansion in powers of inverse and Planck. And so to cancel that leading divergence, what those authors calculated, of course, in the one-loop approximation, is that you need a counter term. And then you impose a condition for that counter term to be diff invariant. And once you impose that condition, you get the full nonlinear counter term that's written there. And this calculation was done in what's called dimensional regularization. What I would emphasize is the coefficient in front of that integral. It's the gamma function. Euler gamma function, which is 2 minus d over 2. So in 4 dimensions, that goes to 0. So that's divergent. That's a divergent coefficient. So capital D is 4 minus 2 delta. So that will be divergent as 1 over delta. And then it multiplies by actually the term that appeared in the anomaly equation. It's a combination of the Euler density and in 4 dimensions what reduces to the Weil square. So that's the d-dimensional writing. So the question is, can you write that in 4 dimensions as a local term? Well, the answer is that if you try to write it just in terms of 4-dimensional gravitational field, then you will end up in a non-local world. In order to write this as a local field theory, you would have to use additional scalar degree of freedom. Or you would need to keep it as higher dimensional term. So here is one procedure, how to reduce it to 4 dimensions. So it's kind of protocol, consistent protocol, how to do that. So you start with n-dimensional metric now, or you know, capital D. Capital D here is 4 plus little n. And you parameterize your metric in the most general way. And then you are careful about all the divergences, because you remember I mentioned there was a coefficient, divergent coefficient in front of the integral. And then from the integral, you would be getting some pieces which are tending to 0 when delta goes to 0. So the combination of 1 over delta and delta will give you some finite answers. And those are the important ones. You need to keep them. And that's the important term that you see. So the sigma in it, so it's all 4-dimensional now. the sigma is a scalar field, and you can see where it's coming from. It's coming from the higher dimensional kind of radian mode, if you will. But entirely now it's written in a four-dimensional context. And the action that you get, it looks a little scary, but actually each term is very special in that action. So the first one is sigma times the Euler density. So you would imagine that term to be present in any theory in which you would like to recover anomaly, because variation with respect to sigma gives you the A term of your anomaly immediately, you can see. The other ones are more subtle because you need those combinations in order to get right anomaly in the end. And those coefficients are all fixed. There is no arbitrariness. The anomaly answer determines exactly what those coefficients should be. Another potential subtlety you might be worried about is that they have higher derivative terms, as you see. Those, nabla square sigma and nabla sigma squared plus nabla sigma to the fourth. And you would worry about your equations of motion being higher than second order, which would be a problem for the Cauchy formulation of the theory of the equation of motion. But turns out they are all very special so that you never get higher than a second order equation of motion. Actually, those terms are known under the names of Galileons. They emerge in very different contexts, and they appear here naturally, so without those discussions of other theories. So they emerge in the context of the theory that Samson mentioned, but also in the context of massive gravity and so on and so forth. They also emerge here. Right? So all of these terms are just like that. Now, they are higher dimensional terms, as you can see, as compared to the Einstein action. And you would then ask, well, Einstein action actually is corrected by a bunch of, actually infinite number of higher powers of the curvatures, which come presumably from string theory or any other version of quantum gravity, if you think about that. And how come then I can even talk about these terms and not talk about the others? So what you will see is that these terms will be suppressed by a lot lower scale in a theory in which you have consistency for these terms. So that scale will separate these terms from other higher dimensional terms which come from alpha prime corrections of string theory, for instance, right? So you could think of them as Planck scale suppressed, while these ones will be a lot slower scale suppressed. And also, I should mention that, as I said, this term was derived by Riegert and Fratkin and Zeitlin, 84, from just very different considerations, just by asking what is it I have to write in order to get the right anomaly. It was derived in the context of the A theorem. There is such a, I won't elaborate, but very interesting work by Komargodski and Schwimmer. They actually independently, as I understand, derived them sometimes later. And then you can also derive these terms as coset. In the coset construction, you can ask, what's the effective theory, what's the Vezumino term of the conformal group quotient with the Poincaré group, right? And this is what you get in that construction, identically. So lots of field theory support. On the other hand, there are lots of problems too, in spite of those nicenesses that I mentioned. And you can see those problems already at the level of classical equations of motion. So if you take general relativity, as we started with, right, and add this term, which captures the anomaly. So this would be analog of what I did in the Schwinger model. Let's say you add that. So you see that the sigma term has no kinetic, a sigma field has no kinetic term in it, because it doesn't appear in the Einstein-Hilbert action, and it appears here only non-linearly. Well, first problem, immediate problem. Let's say you take weak source, some planet, gravitational field of a planet, which is very weak. Well, then you are able to do order by order calculation, and in the leading order for the gravitational field of the planet, you get conventional Einsteinian result, which is written up there, g mu nu equals to 8 pi g Newton times t mu nu. And with that, then you go ahead and substitute into that action to search what is the generated kinetic term for that sigma, and you will find that generated kinetic term for that sigma is actually t mu nu times d mu sigma d nu sigma. That's completely unacceptable. Well, first of all, it's background dependent, but even irrespective of that, the signs are wrong, because you take, so you want kinetic term which is very close to Lorentz invariant term for light cone to be right and for instabilities not to exist. But T mu nu for ordinary matter has very different structure because it has positive pressure, positive energy density. So that would give you some gradient instabilities of that field. So that tells you already that something is very wrong with this theory. The next problem, so I'm going to point out 3 problems. Next one is, actually it's not a problem, it's a big inconvenience, but also such inconvenience signifies that there is something wrong with the theory. And that goes under the name of linearization inadequacy. So ordinarily, we are able to linearize theories around some weak backgrounds, calculate those linear response, and then systematically calculate nonlinear corrections to them. In such theory, you cannot quite do this. Even though you linearize, you find your linear response solutions. Then what happens is that at the nonlinear level, there is an additional constraint imposed on those linearized solutions. Ordinarily, that doesn't happen. Ordinarily, that equation, nonlinear equation, serves to determine the next correction. Here it doesn't. Here it imposes a constraint on the linearized solutions. And it comes entirely from that line, first line, and the fact that you don't have kinetic term for sigma. It's the same origin. So that is that constraint equation. You see, E2 stands for second order Euler density expanded around flat space, and then G mu nu L is the linearized Einstein tensor multiplied by sigma. That's already quadratic, and so on and so forth. That's at least quadratic equation imposed on first order things. So that's a problem, well, indicative of a problem, highly inconvenient. And finally, and probably most physical one, is you can look at the scattering amplitudes in that theory. And the simplest one is to extract the scalar mode, which in D dimensions, I showed you explicitly what it is. And when you look at 2 into 2 scattering amplitude, you will see that it's divergent. So it has a usual structure of the amplitudes. S, U, and T are. It is, yeah. Well, yes, exactly. That's exactly right. This is, yes, Samson is pointing out that this is an effective field theory, but there is a nuance in that. So there are Planck suppressed operators, which you have infinite number of, but all these operators that I'm talking about are at very, very low energies. Actually, they will be at 0 energies, as I'm about to argue. So the point is that this cannot really be effective field theory unless you modify it. So that's the point. And then once I modify, you will see that you will get some consistent effective field theory which is separated from Planckian physics. So that's why we can talk about that indeed, right? Well, so that amplitude is diverging, and you can ask, what's the 4-dimensional Lagrangian decanted right which captures exactly the divergence? Well, it's very simple. I mean, you can write some kinetic term for field, and then the quartic term, which I used already, but the coefficient of that kinetic term goes to 0, right? So if coefficient goes to 0, the way you would see the previous equation is that you rescale that field by square root of sigma, and it will disappear in front of the kinetic term, but it will show up in your coupling, in your quartic coupling, and that quartic coupling blows up precisely because of that 1 over delta square. So that's unacceptable. That tells you that your effective field theory breaks down at arbitrarily low scale proportional to this delta. So how to remedy these problems? It looks like there is almost a unique way to remedy them. What do you need to do? Well, you need to introduce some additional sector which will help to solve all of this or remove all of those difficulties. Now, you don't have too much arbitrariness at your disposal because you have to maintain all the symmetries, but you also have to recover all the anomalies, right? So that anomaly equation is exact. It's any modification that you introduce or generic modification that you introduce will screw up that equation. It will modify that equation. Well, that's not acceptable. And therefore, those conditions restrict very much what you can do. So one option to do that is to postulate that there is an additional sector which is the sector in which there is spontaneously broken scale invariance. It's not nonlinearly realized, and then it can be represented by those 2 terms already at the level of the Einstein-Hilbert action, right? So what I have is the first term is the usual Einstein-Hilbert action, and the next 2 terms is a conformal scalar coupled to Einstein's theory. And it is very important that the second term has the minus sign as compared to the first term. So this capital phi, as I said, has to be related to some nonlinearly realized symmetry, and therefore it has the structure which is some scale m bar, which we don't know at this point what it is, but we will try to understand what exactly it is, times e to the minus sigma. And that signifies the spontaneous conformal symmetry breaking. So this should be taken together with the Rigert action, or the anomaly action that I discussed. In terms of concept, it's very, very meaningful because, as I told you, that Rigert action you can look as the coset of conformal group over Poincare group, actually, and this very much fits into that. Now, what happens then? How all those problems are resolved? Well, they are resolved very easily because the second term, precisely with the minus sign, gives you the right kinetic term for that scalar sigma. That's why I emphasized the sign. So wrong sign for tensor actually gives right sign for conformal mode of that tensor. And that's why it works. So obviously this m bar scale has to be a lot less than the Planck scale for two reasons. First of all, you don't want to flip the sign of the first term, otherwise you won't get Newtonian gravity right. And the second, for reasons that I alluded to, you want all these operators to be suppressed by scale which is smaller than the Planck scale. And indeed, if you go into the limit where m Planck is very large, and you ask what's remaining in the theory, well, this is what's remaining in the theory. You got this sigma with the right sign kinetic term and some higher dimensional interactions, so those sigmas are suppressed by m bar cube. So that minus is a right sign in my notation. So I'm using mostly plus signature, and the correct scalar kinetic term has minus sign in front. So the conclusion is that now you have a healthy effective field theory, which is meaningful below the scale m bar. M bar is well separated from the Planckian scale. You don't need to worry about the alpha prime corrections. However, you do have to worry about these m bar corrections, and you have some leading terms in that m bar expansion, which are precisely specified by those anomaly terms that I showed you on the previous slides. And well, physically, phenomenologically, well, you would say that m bar probably should be about 10 TeV or so. This is some kind of scale of new physics. So there are a number of questions then. Well, first of all, what's about m bar? Can we even go about m bar? Can we complete? Second of all, fine, I mean, maybe for practical purposes, you don't need to think in terms of that expansion, but that extension, but what's the physical consequences of this new dynamical field sigma now? I mean, you've got essentially at this point it's massless. There are lots of constraints on massless fields coming from cosmology, coming from astrophysics, coming from tabletop measurements and such. So we're going to address all of them, or rather go through all of them one by one in the remaining time that we have. First, about the UV extension. And this slide is a little decoupled from everything else that I'm going to say. It's brief. I just wanted to show that such an extension exists for all the practical purposes that I'll be using for cosmology. This slide is not important. So if you don't necessarily get it, it's okay. And it's rather brief also. So I'm glad Eric Verlinde discussed this holographic ADS CFT picture. So it turns out you can embed this theory precisely in that context, in particular in the context of what's called the Randall-Sundrum version of it. And all these terms emerge very naturally, including the terms with the minus sign, phi square r that I mentioned, including the other term, and including the notion of sigma itself. Sigma is, in that context, is related to the radion of two branes in the Randall-Sundrum context. And the benefit of it is that, first of all, you can go to scales a lot higher than m bar. And second of all, you can understand the hierarchy between Planck mass and the m bar mass, which before was introduced by hand. I just put that in. Here, it comes out dynamically. In fact, what you get is that if you think of your compactification radius, which is RC in this context, I call it RC, versus another distance scale, which is the radius curvature of your ADS5. So you need to have RC bigger than radius curvature of ADS5. And then you get the hierarchy because four-dimensional Planck mass will be related to the compactification, I'm sorry, the radius curvature, inverse radius curvature, 1 over L times NC, right? So it's a scale of the curvature times NC, but M bar will be related to NC times that compactification radius precisely. And because RC is much bigger than L, you automatically get that M bar is much smaller than M Planck. So that works very naturally. It's just derivation of it essentially. That's all very good. Physically, it's also interesting because I've imposed the condition that RC is much bigger than L. That means that my Kaluza-Klein modes are actually lighter than M bar. And it had to be like this. If you want to complete something, some effective theory, the scale of, or any scale actually, you better have some degrees of freedom coming in before that scale is reached so that they are softening all your divergent amplitudes. And this is what you see here. Kaluza-Kleins are lighter, and you can show in all, very explicitly that that's a continuation and extension of this theory. So that's what we did with Massimo Porati. All right, so let me now get to cosmology. So what I'm doing here is I'm taking classical equations of motion that follows from that somewhat complicated action. It has in it Einstein-Hilbert term, it has in it that conformal scalar term, and it has in it the anomalous Rieger term that I mentioned all together. And equations are complicated. They're not written here. They are in our papers. But you can focus again on homogeneous and isotropic universe as we do in cosmology, because we believe that's a good approximation. The data supports that that's a good approximation at very, very large scales. Let's say 100 of megaparsec or so. That's a good approximation, right? So the moment you do that, you will see that the Friedmann equation gets modified. So the first line is left-hand side, h squared is conventional Friedmann, part of the Friedmann equation. That's scale factor derivative divided by scale factor squared. And the right-hand side would be something that you would have gotten in conventional Einstein theory, but now you have that term proportional gamma square. So that gamma square is something proportional to the coefficient A that I introduced. It just has pi's and such. So I called it gamma square also to signify that it's positive semi-definite or positive, right? So that's the Friedmann equation. So in principle, well, interesting fact that I would like to point out is that this theory gives rise to what's called the Starobinsky solutions in cosmology. Actually, Alexei Starobinsky, who was a distinguished cosmologist, no longer with us. Actually, he's the one of the founding fathers of many things that we understand about cosmological perturbations and such. Back then, when he proposed the first inflationary model, his solution was precisely a solution of that kind of equation, h squared equals to h to the fourth, but in somewhat similar context. So this one has that solution, but it's not utilized here. So maybe it's a next project we can do at some point. But so the solutions that I'll be talking about are the ones in which that term is a small correction. So these are still solutions which are very close to conventional FRW solutions that we do in ordinary cosmological fits. So the next line is the new equation. Now we have the additional scalar degree of freedom. It comes with the new equation. That's the equation of motion, and it's very special, as you see. It's not just the garden variety scalar because of that conformal nature, the way it was introduced. And it also, that equation also makes connection between this scalar and the conformal factor or the scale factor of gravity. There is a very easy solution of that equation, which is sigma dot equals to h. Dot means time derivative. This is in co-moving time coordinates. So that means that sigma actually is log of the scale factor plus constant. So I know I have these dual notations. A I call the coefficient, but A I also call the scale factor. Those are traditional notations. I didn't want to change. I hope it's not confusing. Whenever I write A of t, that's the scale factor. If I don't write t, that's the A term in the trace anomaly. So here it's the scale factor, and the sigma is log of the scale factor. So essentially that field is the conformal mode, and now it's dynamical. And it participates in the cosmological expansion, as you can see, as long as it's massless. So you find the solutions, we found all of those solutions. They are in the paper and so on and so forth. They are very similar to FRW. The key is how they are different, how this cosmology is different from the one that we ordinarily do without this anomaly piece. Well, it's lots of calculations, which, well, I'm skipping all of them because action is difficult, and then especially when you expand your cosmological background, it's difficult. Nevertheless, it's all doable in certain approximations. So what's interesting is to look at the fluctuations of those fields around those backgrounds. And in particular, I would like to zoom onto one specific problem related to inflation, right? The inflation is the dominant paradigm for us to understand how the structure formed, actually how the universe avoided a bunch of problems of hot Big Bang cosmology, but also how the structure formed through inflationary perturbations. And now I'm telling you that those perturbations will be modified because there is another scalar field which mixes with an inflaton, right? So what I'm doing here, although I'm not showing it, is that I'm taking that theory with the anomaly, and I'm introducing an inflaton in it, as you would ordinarily do in conventional cosmology. And inflaton does, inflaton potential does, nearly de Sitter expansion, and then there is a fluctuation around that potential of an inflaton field, but the inflaton field will mix with this anomalion field, because both are scalars, and there'll be lots of mixing terms. And the question is how that mixing affects the usual perturbation, cosmological perturbation theory. Well, in some approximation, you can diagonalize. And then what you get is that you get 1 degree of freedom, which is mostly inflaton, so it behaves like an inflaton in a good approximation. And then there is another degree of freedom, which is mostly anomalion, and it has very different properties. And what exactly is those properties? So the key quantity that I would like to focus on is the power spectrum. This is just the correlation function at one point of two fields, right? So the first line is the power spectrum for what's called curvature perturbation for conventional inflaton, and that's the conventional answer. In our case, you get very small correction to it, so that's what gives rise to the CMB anisotropies. So you need to get amplitude squared, which is 10 to the minus 9, and that fixes the values of the Hubble constant. The epsilon is a slow row parameter of the inflaton potential, and so on and so forth. The exponent is very small. That's why it's almost scale invariant. So that's all conventional, well-known physics of inflation, first line. The second one is the new part. And as you see, the second power spectrum is very different from the first one. First of all, you should ignore the second term, because that's an admixture of an inflaton, and it's a small correction to this anomalion. But the first one is very different. As you see, it's a blue spectrum. The reason why it's blue is that this k squared divided by scale factor squared, its time dependence gets canceled by that exponent of the anomalion field. And therefore, we just get k squared. And that means that it picks up at shorter scales, smaller k's. So at smaller case, it enhances. Larger case, it's not significant. And that precisely affects the physics. So physically, what happens is that, yes, you generate inflaton perturbations, which go outside of the Hubble volume very quickly during inflation, quasi-de Sitter expansion. And they are huge. They are sitting there waiting for the Hubble volume to grow back and for them to re-enter and affect our cosmic microwave background, structure formation, and so on and so forth. Conventional story. But in addition, now you have other perturbations with power spectrum like so, which at large distances, they are irrelevant because k is very low in that case, so they're not important, so you just ignore as compared to conventional paradigm. However, at short distances, they modify it significantly because the power spectrum can be actually very large. That k squared can come very close to m bar. It can be 1 order of magnitude less than m bar, so you already get 10 to the minus 2 power spectrum, which is gigantic, right? So, plus, these perturbations will be re-entering the Hubble volume a lot earlier. So if you run all the numbers and so on and so forth, you will get that these perturbations will enter during radiation domination epoch. And because they are so large, they can actually lead to the formation of primordial black holes. So I'm just skipping lots of calculation here. We can use what's called the Prachakter formulas. You can convert this into the density contrast power spectrum and so on and so forth, and convince yourself that indeed, once they re-enter, the Hubble volume, they need to grow just a little bit after that to start collapsing into primordial black holes. And all of that will be happening during the radiation domination. It won't be affecting your CMB physics. So here is a quick excursus into that. So that's the mass of the primordial black holes, what you will get as a function of K in this case. You can express this in a function of temperature or this K and so on and so forth. This is to show that once you are in short for smaller Ks, then the typical masses of the black holes you would get will be something like 10 to the minus 18 to 10 to the minus 17 of the solar mass. These are still very small black holes. It's very hard or impossible to form large black holes, let alone supermassive black holes through this mechanism. You'll form small black holes with that mass, but they are above the mass threshold after which they don't evaporate because of the Hawking radiation. If a black hole has mass which is 10 to the 15 grams or less, that black hole won't survive until today because of the Hawking radiation. You need to have more than 10 to the 15 grams, and these are 10 to the 16, 10 to the 17, 10 to the 18, something like that in grams. Right? So then you ask about the abundance. Well, in principle, you can get that vertical axis is the abundance. In principle, you can come close to 1, but it's not. You need some tuning, actually, to get of order 1. If I were to say naturally, it will be fraction of all dark matter, but maybe not 1. With some tuning, you get 1. And tuning is in the tuning of the initial condition of that scalar field. In principle, you can have it, because that initial condition is not determined by any dynamics. Nevertheless, you would need to pick that special number in order to get order 1 primordial black holes as full dark matter in the universe. Now, what I didn't say, and what's relevant for the subsequent slides, is that this implies that this scalar field gets mass at some point later on in the evolution of the universe, and that's where you stop the evolution of this scalar field and producing all the perturbations and such. And it will necessarily get mass, at least from the QCD, as I will show you in the next slide. But there could be other gauge theory, high energy gauge theory, which does the job just like QCD does. And depending what that gauge theory is in terms of scales, this mechanism could be effective or not effective. If it's only QCD, nothing before QCD, then that power spectrum that I showed you will be very small. You won't be producing dynamically those primordial black holes. You have to have some other gauge theory before QCD, which stops that evolution, and then you get naturally that. So here is the theory how it gets the mass, and looks like I'm running a little bit late, but I'll try to finish on time. Well, let's now introduce all the gauge fields back, because that very same sigma anomaly couples to the anomalies of all the gauge fields. Well, at least we know QCD, we know electromagnetism, so we know electroweak, or something beyond. So it couples to the anomalies of those fields. And particular interest is QCD, because it can generate the mass for it. And you have that term of the anomaly and couples to the gauge kinetic term of QCD. And then the story is very similar to what happens to axion. So axion is a pseudoscalar that couples to GG dual. This is a scalar that couples to G squared. Yet there are non-perturbative effects which will necessarily generate the mass for it. And the remarkable thing is that in this case, you can, from general principles, you can calculate the potential of that scalar. And the reason why you can calculate is you can use a trick that that what's called the gluon condensate, what's written there, how it's expressed in terms of lambda QCD. It's something that is renormalization group invariant. And you know the dependence on the coupling constant of that renormalization group invariant object. Now, because you know that, and you also know that introduction of that extra field is just a modification of the coupling constant of QCD, you immediately get the potential for that extra field. And that's what's written on this slide. You see, you have theory in which your effect, so this is assuming that the sigma field is changing slowly. So then your coupling constant gets modified as written in the first equation. And you can then ask question, what's the renormalization group invariant scale, dimensional transmuted scale in that theory? Well, that is what it is, where A effective is a function of the sigma field now, and you can just calculate it. So as a result, you calculate the potential for that sigma, and you get this exponential potential in the equation of motion, And from that equation of motion, you can restore then the full potential, actually. So you would ask again the same question. What is the effective action for that sigma that I have to write in order to give rise to that equation of motion? That's a differential equation that you can solve. And the solution is a very special potential, e to the minus 4 sigma plus 1. So it has a minimum. It starts off as infinity for negative sigma, comes down little negative, has a minimum, and it goes up to 0. So you have a stable minimum at 0, sigma equals 0, and it's massive. You generate mass. As I said, it's very similar to axion, except the potential is not periodic, which is in the case of axion. It's a special potential. And very interesting, Migdal and Schiffman had that potential in different contexts or somewhat related contexts as a 1 pi action which reproduces certain, actually infinite number of word identities in the context of QCD. So definitely there is a connection here, except their interpretation was that this was some kind of global there. Here it's not a global, it's a anomaly on field which has its own kinetic term coming from very high energy physics. And as a result, the mass of that field is a lot lower than the global mass. So it's a crest to a formula which is lambda square, strong scale square, divided by this m bar. Now, you know neither, unfortunately. If you assume that there is nothing above QCD, then that lambda would be the QCD scale. But if you don't assume if there is a high energy scale, then you have a parameter space for that. So you need to explore that full parameter space with observations. So what I have on these plots, taken from those papers and many other papers actually, which address similar questions of phenomenology of a scalar degree of freedom coupled to gluons and then quarks. First one doesn't assume that this particle is dark matter. It's all measurements of either additional force due to the scalar exchange or violation of the equivalence principle. These are tabletop measurements, and there is a multiple of them. I don't know if you can see, the light is hitting this slide, so you may not see, but there are exclusion plots, and therefore that constrains very much that range of lambda and m bar. The second one is, or rather the last two, are the one in which you assume that that particle is dark matter. Because if it's sufficiently light, and well, which is the same statement as this m bar is sufficiently high, then it won't be decaying. It will be very stable or very long-lived, sufficiently long-lived so that it can be dark matter, in which case the constraints are, you get additional constraints from actually dark matter detection in a resonator type experiments in which, well, you put a resonator here and this particle interacts with the photons. You have this particle into 2 photons, and you can convert then that particle in some electromagnetic field into another photon, then which you then detect as a change in power of the equipment, and there are constraints on it, but there are also constraints coming from the star cooling. This RG refers to red giants, and the HB refers to horizontal branch of the star evolution, and so on and so forth. So you get significant constraints, but it's not too much constraint. You still have large parameter space. So we are this work is still in progress. We are looking for more constraints which could tie down these things. And actually, I was thinking of pulsars. Maybe speaking of Jordan, maybe pulsars can, magnetic fields of pulsars can constrain somewhat, and definitely we will look at something like this. So just conclusions. There is a unique effective field theory of gravitational trace anomaly. When I say unique, the only ambiguity which I didn't introduce was the cosmological constant. I always assume the tuning of the cosmological constant, which is a problem by itself. Other than that, it's unique. And that requires some scale m bar at which some new physics is taking place. We know it has to be some spontaneously broken symmetry phase. And there is one explicit example of that I showed you that was in the context of holographic ADS picture. That setup gives you precisely the spontaneous breaking of conformal symmetry in the dual CFT. So there is, as a result, there is an extension above m bar if you care about that. But for practical applications, let's say in cosmology and astrophysics, you just have this new degree of freedom, which is massless in the early universe. It generates additional fluctuations. Those fluctuations can be strong in the early phase. During radiation domination, can collapse into black holes if it stops fluctuating, it gets mass at high energy scale, then that's very viable scenario. You can have those primordial black holes. If it doesn't have that QCD, ordinary QCD will give it a mass, but in that case, power spectrum will be weak. You won't get primordial black holes. However, you will get this particle as a dark matter particle because it will be just light particle with tiny decay rate, which makes it stable for all practical purposes. That's it. Thank you.
Thank you. I think that many elements of this, like when I was younger, I was thinking about it. Was very,
sure.
very, very happy that I see it's still alive. Questions, please? Yes?
Thank you for the very interesting presentation. You talk about primordial black holes. What do these black holes look like in this theory? How do they differ from GR?
Okay, so that's good. So somebody looked at general black hole solutions, classical black hole solutions. They do get here because of this fifth force. So you would expect those primordial black holes would also get that here, but that's a small correction. So in the leading approximation, they are very similar. In terms of their fifth force effect, they are very similar to GR black holes. So for the primordial purposes, that difference wouldn't make supermassive black holes, yes. So you would get those solutions. You would have some elements of fifth force, which is very small, actually. So that fifth force will be suppressed by some fraction of m bar over m Planck into some power. And there is a work by a Japanese author, which I can point out to you, so that, yeah, there is a solution.
Thank you for a great talk. I have perhaps a somewhat theoretical question. So you were speaking about this gravitational anomaly and the associated degree of freedom. And if we had a theory with several different anomalies, like for instance a gravitational and a chiral, which is not like cancelled, then would we have a degree of freedom per each anomaly, or how would that play?
Yes. So I discussed the minimal scenario in which I said that one field recovers all the anomalies, gauge anomalies, gravitational anomalies, everything else, the most minimal one. So in principle, I thought a little bit about it. I think it's possible to have multiple fields responsible for various anomalies. But so if I understood correctly your question, yeah.
But how is it decided? One field, many fields? Is it like, what's the principle which would tell us, or is it different theories where those?
Well, if you manage to construct those theories, which I'm not sure, if you manage to construct those theories, yes, then it will be different theory. Well, observationally will be different because you will have more fields. But for many reasons, I think this is preferred, not only because minimality, but you have explicit construction, while in the other cases you need to worry about how you get one and you don't get the other one, and it seems like there is some contrived way, but I've never written it up because it was very contrived. Yeah.
Do we have any implications for gravitational waves from here, like?
Right. So the implication will be, sorry. Well, yes, if you look at this, as you can see, if you look at the second term, for instance, right, if sigma has a background, the first term is linear in gravitational wave. So in the equation of motion, you will have, let's say, g mu nu times something, and then if sigma has a background, it will modify. But modification will be very small because it will go by kind of power of energy divided by this m bar. So it very much depends on M bar, and typically we would assume that M bar is a high energy scale. I mean, we're thinking, I don't know, about 10 to the 10 GeV or something, or even higher. So that will be small. There will be modification, but small. But that kind of phenomenological question one should explore if you can push the limits and see if there is anything interesting coming out of that. Short answer is a yes.
So basically, I mean, the example of Polyakov's 2D gravity, when you have this Liouville thing and so on, it is actually direct analogy, or
Yes.
it is basically...
This is the exact
absolutely the version of it in 4 dimensions.
Yes. So yeah, thank you for that point. So in two-dimensional case, bosonic string theory case, the Polyakov action has that additional scalar, but it's a very simple theory. It's d sigma squared plus sigma times Ricci scalar. That's it. And this is the generalization of it, and as you can see how complicated it is compared to Polyakov. The reason why this is the same is because if you do the coset construction, which I didn't discuss, conformal group over the Poincare group, you do 4-dimensional construction, you get this. You do 2-dimensional construction, you get Polyakov action. So they are really the same thing in different dimensions.
So in a sense, the gauge version of it would be that Vesumina thinks that I was working with.
So if you
that
gauge
would
it, yes.
That would be gauge. This is a gravitational version.
That's right.
The main concern in those days was normalizability and all these kind of things.
Yeah.
So is there some kind of argument you can run that there is if you fix certain energy below energy scales, there will be no mixing, that you actually have a gap that you can control it?
Yes. So as an effective field theory, as I mentioned, it's a consistent effective theory. You
as effective, I understand, but as a quantum?
But there is also extension beyond that scale in this case, you see? It's just ADS5, Randall-Sundrum with some boundary, very special boundary CFT.
Yeah, so, I understand now. If you go that way, so yeah. Okay, I understand.
So, well, that's a completion.
I was not joking when I said that this is something that there was a dream long ago, how to do similar to what Polyakov did with Liouville in higher dimensions and so on, and it seems to me that it's actually very relevant to physical questions today. Okay. Yeah. Thank you very much. Let's thank Greg again.